there, but we like to.
All right. Okay.
Flip it on or put it in your pocket.
Ready to go?
Yep.
All right, so for the afternoon session, we're happy to start another set of lectures from Daniel Baumann. This is Primordial Cosmology.
Okay, thank you very much. Thanks for the organizer to inviting me. Whoop. Yeah, so the last time I lectured was actually 8 years ago at TASI. It was a lot smaller than this. I think that TASI was like an experiment of having young people lecture or something like this. So I'm glad to see that we didn't destroy the TASI enterprise by that time. And it seems to be a factor of 2 bigger, I think, than, well, at least it was a smaller room last time. Okay, so I've been asked to talk about cosmology generally, in fact. Of course, cosmology is a very big topic, and it's not possible to cover all of cosmology. So I decided to narrow it down to primordial cosmology. But even primordial cosmology, of course, has many facets, and so I don't have a chance to talk about all of these things in 4 lectures. So what I decided to do, the one way of focusing myself, was I want to discuss 2 primary ways in which cosmology can test for new physics. Okay, so of course we all would like to hope that there's new physics beyond the Standard Model to be discovered. I'd like to argue that cosmology is a very promising way of searching for that new physics. And as I'd like to explain also in the 2 parts of my lectures, that there are essentially 2 complementary ways in which we can look for these new physics signatures. And so I've tried to sketch it out. Not quite sure where's the best place to put this.
Where your collar is, it might be a little easier to get it.
Okay. Is that good? Yeah. Yes, I've tried to sketch out these 2 complementary ideas for testing new physics. So essentially what we do in cosmology is when we make observations, we typically express those observations in terms of cosmological correlators. So this is what I'm showing here. So there's a correlation function, endpoint correlation function of cosmological observations, which might be observations of the temperature fluctuations in the cosmic microwave background, the distribution of galaxies on the sky, things like this. There are many different types of cosmological observations. And we typically express all of those observations in terms of correlation functions. And then we have ways in which we can trace these late time correlators back to initial conditions. So that's what I'm illustrating here. And we typically express those initial conditions as fluctuations in the metric. So this variable zeta here is called the curvature perturbation. So those are is basically fluctuations in the 3-dimensional Ricci scalar on the initial spatial slice. And again, we try to describe those fluctuations in terms of statistically, in terms of these endpoint correlation functions. And so then there are 2 ways in which new physics can affect this picture of going from initial conditions in the curvature perturbations to late time observations. It can either affect the evolution of these fluctuations through changes in the equation of motion. And so this is what I'm illustrating up there. You can modify the right-hand side of the Einstein equation by adding extra stress energy, new particles as we're going to be seeing. Or the evolution equation for the matter fluctuations can be modified through a change in this conservation equation here. You may even want to modify the left-hand side of the Einstein equation, but that's blasphemy, so we're not going to be doing this in these lectures. Okay, we're going to keep Einstein gravity intact, and we're going to be adding new matter sources and ask how those new matter sources can affect the evolution. So that's one way. The second way is trying to modify the initial conditions directly. So maybe I should clarify what we mean by initial conditions in cosmology is the initial conditions at the hot Big Bang. So that might not be the beginning of the universe. It's just when the universe first came into thermal equilibrium, and we can specify fluctuations on those initial surfaces when the universe became this thermal state. And so that's what we define as initial conditions. We typically believe that there's a phase before that hot Big Bang phase, which we describe by inflation. In that phase, we think dynamically generates initial conditions for the hot Big Bang. Okay, so there's a probability distribution function from which these curvature perturbations will be drawn. That probability distribution function can be changed if I have additional physics operating during inflation, for example. And so we're going to discuss different types of physics that we can have during inflation, changing the initial probabilities and changing, therefore, the correlation function of these curvature perturbations. Okay? So that's it, basically. Roughly speaking, constraints in cosmology and ways of testing new physics divide into these two classes. Yeah, you change the evolution or you change the initial conditions. And so then the two parts of my lectures will be, first, we want to study some of these evolution effects. So we're going to be starting in the hot Big Bang and ask, how can I change the evolution of the hot Big Bang equations? Okay. I'm going to start very basic today, just to put everybody on the same page, define my notation and so on. So I'm going to give you a very short review of Big Bang cosmology. I'm going to then describe a little bit one of the most important cosmological probes that we have, which is the cosmic microwave background. And so I'm going to give you a primer of cosmic microwave background physics for particle physicists. Okay? So I'm going to tell you just enough so that we can discuss a little bit how changes in this evolution can affect what we see in the sky. And I'm going to give some examples of if we have extra light particles in the early universe, how do they affect this cosmic microwave background radiation. So that's going to be, roughly speaking, the first two lectures. And then in the final two lectures, I'm going to talk about inflation. We're going to be deriving in a lot of detail, in fact, the quantum fluctuations produced by inflation. If you haven't seen that calculation before, you will have to see it. In fact, I think Juan Malacena once told me that you have to be able to do this calculation in your sleep. If somebody if somebody were to wake you up at night and ask you how to calculate the two-point function of fluctuations in de Sitter space, okay, you'll have to be able to do this. And so my task is to make you get you to that state, that I could wake you, and you will have to be able to do this. Yeah. So first, this calculation is going to be done just for free fields in de Sitter space. Okay, very simple. We're going to then add interactions to this picture. Those interactions will lead to higher point correlation functions in these quantum fluctuations. We're going to calculate those. And then we're going to see how extra heavy relics will affect those calculations. Okay? But that's going to be in the second half of this course. Okay, any questions so far? So I should say I'm very happy. I'm, in fact, more than happy to take questions in between. If you don't ask me questions in between, I have the tendency of speaking faster and faster and faster until I break. So it's really good to ask me questions in between. Yeah?
So who will wake Juan at his sleep?
Sorry?
Who will wake him at his sleep?
If you give me your phone number, I will call you. Okay. Okay, so let's start with part number one, which is relics from the hot Big Bang. And in fact, before we start, let me give you a very rough sketch, just an order of magnitude estimate, illustrating why cosmology is powerful and in fact will soon supersede other probes that we have for this type of physics. So what we will be interested in is light particles. And light meaning with a mass scale of order the neutrino masses or even lighter than that. Okay? So you might think light particles are very easy to produce in colliders. Why don't we know the light particle spectrum of the universe extremely well? And of course the answer is, just like for neutrinos, these particles can be very weakly coupled. So if I have light but weakly coupled particles, and so here what I mean by light and weakly coupled is in reference to neutrinos, for example. So these are particles that could be lighter than neutrinos and even more weakly coupled than neutrinos. And if they're very weakly coupled, in fact, they become relevant very early in the history of the universe. So by studying very weakly coupled particles, we're also going very far back in time. However, because of this weak coupling, they're hard to produce. In colliders. Essentially because they have very small cross sections. So colliders might not have enough luminosity, might not be producing enough interactions frequently enough to produce these particles at a sufficient rate. Okay. So this is what makes particle physics in principle blinds to these type of effects, and we have to look to astrophysics and cosmology to try and learn something about this type of new physics. So astrophysics and cosmology. Is sensitive to these particles. Through either, because we are able to probe environments with very large densities, and or we're able to follow physical processes for a very long time, so long time scales. Okay, so to illustrate this, imagine we have a two-body scattering. So there are two particles coming in. These particles scatter into n particles going out. And at least one of these particles is some new light and weakly coupled particle X that we've never seen before. Okay, so such a process would be described by a Boltzmann equation. Okay. But just at an order of magnitude level, we can integrate that Boltzmann equation over momentum. That will tell us the rate of change of the number density of incoming particles as a function of time. And so just order of magnitude, we can write delta n over n, so the fractional change in the number density of incoming particles, for example. And that's n times sigma, cross-section for this process, times delta t. Okay, so this fractional change in the number density is simply proportional to the interaction rate. So number density times cross-section gives you a rate, times the interaction time. Okay, that gives you the number, this dimensionless change. And so from this expression alone, you can see why high densities and long time scales are able to overcome small cross-sections. Okay, because they enter in this change. So if I'm able to monitor this rate of change in the number density of incoming particles as a function of time in very high density environments, and then maybe I can follow it for a long amount of time, I become all of a sudden very sensitive to extra species that are being created. So for example, processes like this happen inside of stars. So one example is so-called stellar cooling. So if we just have the standard model and none of these extra particles X, we know how stars evolve, and we know that they have to cool at a certain rate. So it's dangerous to have extra light species that are produced inside of the centers of stars, and changing the behavior of stars over long time scales. Okay? So in particular, a typical density inside of the star can be estimated simply as the cube of the temperature at the core of a star. Anybody has a guess what the temperature at the center of a star is? Every string theorist has to know this. Yeah? A million. I don't even know in degrees. Can you tell me in EV? That is probably true. I also had to look this up. So it's actually about 1 keV. And Google will tell you how much Kelvin that is. Okay. So in natural units and so on, this is about 1 keV is the temperature at the center of a star. So the number density at the center of a star is, of course, the cube of the temperature. And then the lifetime of a star is about 10 to the 16 seconds. Okay. So you can then ask, how big does the cross section have to be, given those two estimates, to get an order 1 change here in the fractional number density of particles inside of a star? And that turns out to be for cross sections that are bigger than about 10 to the 10 GeV to the minus 2. Okay. So this is very weak couplings, but the fact that we can follow the lifetime of a star for such a long period of time, 10 to the 16 seconds, that's really what's giving us this gain. So particle collisions inside of a collider are like, I don't know, tiny fractions of time. Time scale is very short inside of a collider. While inside of a star, we can follow this change in this rate of particle production over a long period of time. and that will accumulate into a change in the evolution of a star. That's not what we see. Okay, so that's why using that kind of argument, you would put bounds on the cross sections of these extra particles at the level of about 10 to the 10 GeV. Okay, and that's an enormous energy scale. So it's interesting that astrophysics can allow you to go far beyond the energy scales that are probed at the LHC, for example. Another astrophysical example. Yeah.
So obviously we haven't followed any particular stars for 10 to the 16 seconds. So you might have to make some assumptions over the stars that you're observing as far as their length. How do you know that?
Yeah, so you actually do this statistically. I think you're trying to make sure that you don't have big deviations from the standard Hertzsprung-Russell diagram of a star. So I'm no expert on this, so the details is...
So let's push a little bit harder on that. I mean, there's the Hertzsprung-Russell diagram, but on the other hand, there are parameters that go into that. You know, you haven't done the first principles calculus.
Very good, yes.
Okay.
Very good. So maybe I should use that as a motivation to say that the type of constraints that I'm going to be getting from cosmology will have a more first principles flavor to it. Okay, so in that sense, it's very true. The stellar modeling is quite complicated and so on, and so there are complicated codes like MESA or something like, or Mensa or something like that calculate that, and so you can add to these codes extra rates from extra particles and then feed that through and get constraints. That's, I think, what people in practice do. In cosmology, we'll be able to do this pen and paper like, so it's much easier to understand these things. Another astrophysical effect that's even harder to model than the evolution of stars is the explosion of stars. So we can have supernova explosions. The time scale of a supernova explosion is much shorter, of course. Typical time scale is about 10 seconds. But the local temperature that I'm creating is much higher, and so the number densities are higher. So the typical densities in the environment of a supernova explosion is about 30 MeV cubed. And it turns out that this gives you roughly similar constraints. So in supernova explosions, you gain by the fact that temperature is high and you have higher densities, and that overcomes the fact that you're only following this process for a short amount of time. Okay, and then the combination of these two things happen to be roughly the same as for the evolution of stars. Okay, so those are the two main features that people use in astrophysics to put constraints on extra light species. So we'd like to compare this to cosmology. So in cosmology, I have the opportunity of looking at very high density environments at the early history of the universe, shortly after the hot Big Bang. So the densities can be much, much higher than 1 MeV cubed. As we're going to see, 1 MeV is about 1 second after the Big Bang when neutrinos decoupled. And we're going to be talking about epochs in the history of the universe earlier than that. So as I go to very high temperatures in the early universe, I gain by making the density very high as a cube of the temperature. But I lose by the fact that the time scales become shorter and shorter. And I think it goes quadratically with temperature. Yeah. So the combination, because the Hubble rate actually goes as the square root of density, and the density goes as temperature to the fourth. So it's the square of temperature. We're going to see this in a moment more clearly. But so the time scale gets shorter as inverse of the temperature squared. But we still have 3 powers of temperatures and density. So we will still win by going to higher and higher temperatures because the density grows faster than the time scale goes down. So typically here we're looking at time scales that are less than a second, but we will still win by the fact that the early universe is very dense. So it turns out, if you do this order of magnitude estimate, that cosmology will beat astrophysics. For temperatures that are larger than about 10 to the 4 GeV. Of course, that will depend slightly on details on what type of particles we're looking for and what type of reactions with what kind of couplings it has to the standard model. But just at this order of magnitude level, this is what you find. Okay. Okay. So what I want to do, this is just to sketch out where most of this power in constraining extra physics comes from, and what I want to do in the rest now is kind of flesh this out a little bit more. Okay, and so in order to do this, we have to step back, I'll have to give you a very quick overview of basic Big Bang cosmology, thermodynamics in an expanding universe, and those kind of things. I'm assuming all of you have seen this before in cosmology courses, but maybe not remember all the details. I'm going to sketch out the things that are going to be important for our story. Okay? Any questions about this? Okay, so then let me start by reminding you of the Big Bang. Okay, so if you think back to your first cosmology course, I don't know how long ago that was, the starting point of any discussion in cosmology is, of course, defining the space-time metric of a homogeneous universe. So let me write it down in my favorite notation. So the metric ds squared is minus dt squared plus a squared of t dx squared. Okay. So we have introduced a scale factor here that describes the expansion of the universe. We have defined three-dimensional spatial slices. Okay, and most of these lectures, or all of these lectures, is going to be specializing to the case where these slices are flat. Okay, we have very good observation now that this is the case for better than a % level accuracy. Okay, so in order to be able to do Fourier transforms with not nasty Bessel functions and so on, we're going to be specializing to a flat universe. We're also often going to be rewriting this metric in terms of so-called conformal time, and I'm going to be using the letter tau to denote conformal time. Conformal time, as the name suggests, has a nice feature that it transforms the metric into a metric that's conformal to Minkowski. So it has the scale factor becomes an overall conformal factor of time, and we have a effectively two-dimensional line element of Minkowski space that's spanned by the conformal time coordinate and the spatial coordinate x. And the reason that's convenient is because, as you know, of course, light travels on null geodesics, and so the light rays won't actually feel this overall conformal factor, and so they will travel in a space-time geometry that is just given by this effective Minkowski space. So all of the intricacies of the expansion of the universe have been transformed away by going to these conformal coordinates. Okay. So then we have co-moving coordinates of space and conformal coordinates of time. And we can describe the causal structure of the universe, for example, in a very simple way, because it's the same as this effective Minkowski space. Okay. The next thing you have to do is you have to discuss the time dependence of this scale factor. So you talk about the dynamics of the universe. And of course, that's given by the Einstein equation. But because of the high degree of symmetry of this space-time, so everything has been, the 10 independent components of the metric have been reduced to just one time-dependent function. Of course, that's a great simplification. And also the equations of motions become highly simpler than the Einstein equations. So in particular, we get the Friedmann equation, which tells us how the rate of change of the scale factor with conformal time is related to the density of the universe. So there's 8 pi g Newton divided by 3 density times the scale factor squared. Okay, so this is the Friedmann equation. To complete this equation, of course, I have to tell you something about the evolution of this density parameter. And so this density rho will evolve as a to the minus 3 if the universe is filled by matter, and a to the minus 4 if it's filled by radiation. Okay? For matter, this a to the minus 3 is simply the fact that the volume of the universe expands and the number of particles inside of the box stays the same. Okay? So this is just a volume dilution factor. Radiation, there's an extra dilution because the radiation inside of a box redshifts and loses energy. So energy per volume then goes down slightly faster. So if I were to feed these scalings into the Friedmann equation, I can then solve for the scale factor a of tau, and I find that it goes quadratically if the universe is filled purely with matter, and it goes linearly if the universe is filled with radiation. Okay. So dividing things into matter and radiation is very coarse. This is basically a division by how much pressure this energy component carries. So matter is pressureless, while radiation has 1/3 of the energy density as its pressure contribution. But we can subdivide matter and radiation into different components of the Standard Model, of course. So let's ask, if we look at the particles of the Standard Model, how do they behave? So I'm going to call this the cosmic inventory. So of course we have photons and neutrinos. Neutrinos have a small mass, but for most of the history of the universe that mass is irrelevant. And so neutrinos and photons behave as radiation for almost the entire history of the universe. We then have electrons and protons in the early universe, and then also slightly heavier elements like helium and lithium and so on, but we're going to be ignoring those for most part. So electrons and protons collectively are called baryons. Okay. Of course, electrons are leptons, but most of the mass in this electron-proton system is carried by the protons, and that's why we call them baryons. Okay. If you're upset by this, you should ask your astronomer friends what they mean by metals. Okay. So metals is everything that's not hydrogen for
Or helium too, right?
Sorry?
Anything that's not hydrogen or helium?
Maybe. Okay. Just as bad. Okay. Then we also know, of course, this is not really quite part of the Standard Model, but we know it exists. So we have cold dark matter. Plays a very important role in the history of the universe because it carries most of the gravitational influence at late times. And so collectively, those three components we call matter. And so I also want to entertain the possibility that there could be something that we have been missing so far, some new particle species X. Okay. But the Standard Model lives here, and then we might have something else, and I will discuss how we can look for these extra components. Okay, so let me just review a little bit of the thermodynamics of these different components. So for each species, A, we have an energy density rho A, and this energy density can be written in terms of an integral over momentum eigenstates of the distribution function. So that's the probability of a momentum eigenstates being occupied. So that's this distribution function f of A. It can be a function in principle of space, momentum, and of time. And then that integral has to be weighted by the energy of each of these momentum states. Okay? So this is roughly the probability of the state being occupied times the energy of the state, integrated over all possible momentum states gives you the density. If I don't forget that there could be a degeneracy of states, for example, if the particle carries spin. Okay? So for a spin-1/2 particle, you would put a factor of 2 here. For a photon, you put a factor of 2 as well for the two polarizations, and so on. Okay, so then we just need to know what is this distribution function. So in equilibrium, this distribution function takes a maximum entropy form. So f of A. So first of all, in equilibrium, when the universe is homogeneous and isotropic, the distribution function itself cannot depend on x, and it cannot depend on the direction of this momentum of the particle. So it can only depend on the magnitude and on time. And so in particular, magnitude can be traded for energy. So this f will just become a function of energy and of time. And the explicit form is e to the energy over t plus or minus 1. If I choose the plus sign, I get the distribution function for bosons. If I choose the minus sign, I get the distribution function for fermions. Okay. Sorry?
So which time, t at which time do we think that?
I'm always going to be using this conformal time t. Almost never.
No, I mean
Yeah.
Temperature, the capital T.
Yeah. This temperature is in fact is a measure of time. Okay? And so because it's monotonic, the universe is cooling, so I can trade time for temperature. There's going to be a specific relationship that we're going to see in a moment maybe. And so both energy and temperature actually depend on time. It actually turns out that if the particle, unless there's strong scatterings, this distribution function has to be preserved. Okay? And so since it has to be preserved, energy and temperature have to evolve in the same way. And we're going to see in a moment that there's a specific event in the history of the universe where that's not the case for photons. But for most particles, for most of the history of the universe, that's the case. And so if the temperature goes down by 1 over the scale factor, the energy also goes down by 1 over the scale factor. That's the standard redshifting of energy and temperature. Yeah?
If the universe is very young, also like muons and tau would be so
Yes?
why we don't consider them?
Yeah, we do. I could have included. It depends on what I basically meant by this inventory is actually what survived until today. It's true. Yeah, good point taken. Yeah, you could have enlarged. Of course, the standard model has more particles than what I have written here. All of the particles of the standard model existed in the early universe and have to be taken into account, and we will take them into account in a moment. Yeah. Any other questions? So there are a couple of qualitative features that we can recognize immediately just from this expression. The first feature that we see is that if the temperature is much smaller than the mass of a certain species, so for example muons, yeah, if I'm at a temperature where the temperature is smaller than the mass of the muon, then the energy density of this species becomes exponentially suppressed. Okay?
The plus and minus should be minus for
Is that all right? Yeah, I guess so, because it has to. Yeah. It has to, yeah. Okay. All right. Thanks. Okay, so at temperatures below the mass threshold of a certain particle species, the energy density becomes Boltzmann suppressed, while for temperatures above the mass of a species, we can ignore the mass and treat them effectively as massless. Then we can just do this integral, and what you get when you do this integral is an answer that's proportional to temperature to the fourth. Okay, that had to be the case because if we just do dimensional analysis, we want to get energy to the fourth as a unit for energy density. But the only mass scale in the problem when the temperature is very high is just temperature, because the mass is becoming irrelevant. So it has to scale as temperature to the fourth. We knew that. It also has to be proportional to GA, the number of degrees of freedom. And then the only thing that this calculation really tells you is that the constant of proportionality is pi squared over 30. Okay? Oh yeah, and then it should be 1 for bosons and 7 over 8 for fermions. You can also show, I haven't actually shown you the expression for the pressure of this gas of particles, but if you were to consider the expression for the pressure, then you would be able to show that in this limit the pressure indeed becomes 1/3 of the energy density, and it's correct to call this radiation. That's the definition of what we mean by a radiation component. Okay? So what have we learned from this? One thing we have learned is that matter is radiation dominates. So at any given temperature, if I just wanted to count the dominant contributions to the energy density, in equilibrium it's just radiation that has to be counted. Okay, so radiation dominates. And the total radiation density, rho r, is therefore just the sum of all components with temperature bigger than the mass. Okay? And so it's conventional to write this as pi squared over 30 times some weakly time-dependent function g star, which I'm going to be defining in a moment, times t to the 4th. This g star of t is simply the sum of all bosonic degrees of freedom plus 7/8 the sum of all fermionic degrees of freedom. Okay. So what the reason this is time dependent is that as the universe evolves and cools, this condition of course changes. More and more particles will start to become non-relativistic and shouldn't be counted here in the sum over all relativistic species. And so therefore this G star is often also called the effective number of relativistic degrees of freedom. Okay. So for the standard model, as a function of time, temperature, so if I have high temperatures here and low temperatures here, so the universe cools this way, how many degrees of freedom does the standard model have? Any guess? So at very early times, at high temperatures, all of the degrees of freedom of the standard model are relativistic. We should be counting them in this sum here. What would I get if I do that sum? Roughly 25. Who thinks it's larger than 25? Okay. Yeah. So it turns out that it's 106.75. Okay. So it's a fun exercise to actually, fun depending on your definition of fun, but it's maybe a useful exercise if you didn't get this number to actually do this counting. And what you have to keep in mind, of course, is that, for example, electrons, you have to count the 2 spin degrees of freedom for the electrons, so you get a factor of 2. You also have to count antiparticles, so you get another factor of 2. So electrons by themselves already have 4 degrees of freedom. Then we have three generations, so we have to multiply by 3 if you want to get electrons, muons, and taus, and so on. Sorry, and then 7/8 is exactly good because it's fermions. Okay, exactly, and that's why you can get something fractional. Okay, because of the 7/8. Good, you have to count those as well. Exactly. So that's why you get factors of 3 and so on. Okay, so you quickly can get something large. So actually, there's a large number of degrees of freedom in relativistic species in the early universe, 100. Okay, and so then as the universe evolves, you get these steps in this function because a certain particle species, for example, the first particle that becomes non-relativistic is the top quark. Okay, and so as the top quark becomes non-relativistic, it drops out of this equilibrium, and I shouldn't be counting it, and so the energy density in radiation decreases by these steps. Okay, so I won't go through all the steps of all the particles of the standard model, except to mention that there's one important step that happens here, and this is in fact going to be important at some point later in the lecture tomorrow, where the number of degrees of freedom drops from about 70 to about 10. Okay, and then it drops from 10 to about 3.4. Any idea what happened here from 70 to 10? Why did we have this sharp drop in the number of degrees of freedom at some point in the history of the universe? Exactly. So this is the QCD phase transition. So at temperatures above this scale here, all the quarks were free particles and had to be counted as individual relativistic species. Then there was confinement, so the quarks combined into hadrons. And in fact, so of course there are many hadronic species that were being created, but most of them are very massive. And the only one that was light enough to still be relativistic is which one? Pions, exactly. So you just count the pions. So at this point you're only counting pions, electrons, photons, and neutrinos. Okay? What happens here? Muons, yeah, exactly. Okay, there was one more step, which is the muons, which I've ignored here. This final step here is the fact that the temperature drops below the mass of the electron. Okay, so this is also often referred to as E plus E minus annihilation. Okay. All right. So this describes for us, what happens in the equilibrium story in the history of the universe. Okay, different particles become non-relativistic, and then their contribution to the energy density becomes exponentially small. So if equilibrium had persisted for all the history of the universe, that would be a disaster. Okay, because then the universe today would just be photons. Okay, and you can't do much with just photons. Okay, so in order to have the kind of the complexity that we see around us, it's important, of course, that the universe, certain phases in the history of the universe were non-equilibrium phases. So time scale? Yeah, so this, okay. A good thing to remember is the relationship between temperature and time in cosmology. I think it's, so if you normalize temperature by an MeV, and you normalize time by a second, then the constant of proportionality is 1. And you just have to know that the scale factor in a radiation universe is there's a square root here. And let's see, do I need to put it inversely? Yes. Okay? So that's just the proportionality between time and temperature. And so you can pick your favorite event in the history of the universe in terms of energy scale and relate it to time scale. So for example, 1 MeV is 1 second. That's a good thing to remember. Everything else follows by just this proportionality. But actually, I should have mentioned, so I put very detailed notes on, at the moment, still on this web page, cosmology.amsterdam.tasi. At some point, I will figure out how to put them on the wiki. And so you will see, much nicer graphs of this coming from actual computer calculations and so on, with units and so on. And so those things you can find there. Okay. And I will also later use those notes to be able to shortcut some of these calculations that I plan to do. Okay. Just because we won't have enough time to go through the details. Okay. So in order to describe parts of the history of the universe, it's important to go beyond this picture of just equilibrium. The way we characterize whether something is in equilibrium or not is we compare the interaction rate of a certain process with the expansion rate of the universe. So the expansion rate is the Hubble rate that we have seen appear in the Friedmann equation earlier. And so if interactions are very frequent, more frequent than the universe is expanding, then we are on the conditions of equilibrium. Okay? While if the interactions are small, then the expansion of the universe is so fast that it stretches particles apart before they can react efficiently, and so that will be non-equilibrium. And so of course there usually is a crossover. Usually at high temperatures interactions are very efficient, and so at early times things are in equilibrium, but the rate at which the interactions drop with temperature is usually faster than the expansion drops. And so at some point you will cross from equilibrium to non-equilibrium, and this crossing point is called decoupling. Okay? So if you want to very roughly understand the history of the universe, it's important always to make this comparison, order of magnitude. You compare the interaction rate of a certain process with the expansion rate, and that will tell you whether something was in equilibrium or not, and at which point something decouples. Okay? And decoupling is important, as I said, because then it's not the case that we only have photons. It's because of these decoupling events that certain things survive, even though their masses would tell us that they wouldn't be surviving that long. All right? Okay, so let me give you 3 important examples of this. The first example is the decoupling of neutrinos. So the interaction rate of a neutrino species is given by Fermi's constant squared times temperature to the 5th power. Okay, so that's just dimension analysis. If I ask what's the cross section for or the matrix element for a weak force interaction is given by Fermi's constant, and I have to square it to go from an amplitude to a rate. And then in order to make up units, I'm putting temperature scales. Okay, so this tells us the rate of interactions of neutrinos with the standard model at early times. I compare this to the expansion rate. The expansion rate is given by temperature squared divided by the reduced Planck mass. Okay, so this temperature squared comes from the fact that I had temperature to the fourth for radiation, but in the Friedmann equation, the radiation enters linearly compared to h squared. So to make it h, I take a square root, I get temperature squared. Okay. So if I do this comparison, I will find a critical decoupling temperature of about 1 MeV. And as I showed you there, 1 MeV corresponds to 1 second. So if you can detect the effect of these decoupled neutrinos, we will be able to look for at the moment 1 second after the Big Bang. Okay. And I'm going to show you in a moment how we have detected this decoupled species. Okay. So shortly after neutrino decoupling, what happens is electron-positron annihilation. And that's relevant because it will lead to a difference in the way neutrinos, the temperature of the neutrinos evolves and the temperature of the photon evolves. Okay. So if I draw a plot of temperature versus scale factor, the temperature of the neutrinos dilutes just as 1 power of the scale factor, 8 to the minus 1. So they're simply free streaming. It's just a geodesic evolution of of the neutrino trajectories. Okay. And you can show from the geodesic equation in a expanding space-time that energy goes down as 1 over A, and the distribution function stays frozen in because the species are decoupled. So temperature has to go down by a factor of A as well. Okay, nothing happens to these neutrinos except that they dilute like radiation. Okay, while the photons will trace out a temperature that looks something like this. Okay. So at the beginning, so if this was neutrino decoupling, this particular moment here is E plus E minus annihilation. So what happens at this annihilation is that the energy in electrons and positrons and the entropy in electrons and positrons get transferred to the photon gas, but it doesn't get transferred to the neutrinos because the neutrinos have decoupled already. And that leads to a slight effective heating of the photons relative to the neutrinos. Of course, there's no absolute heating. Both of them are cooling, but photons will cool slightly less fast than the neutrinos do. And so in the end, what you're left with, and then after this process is completed, this thing again goes as 1 over A. Okay, 1 over scale factor. So there will be then at the end of the day a splitting in the temperatures of photons and neutrinos. That's computable. And so I'm computing it in the notes, but here I just give you the answer. So the answer is that the temperature of the photons is larger than the temperature of the neutrinos by a famous factor of 11 over 4 to the power 1 over 3. Okay? And so this translates, for example, given that we have measured this today, we know that the temperature of the photon bath is 2.7 degrees Kelvin. The temperature of the corresponding neutrino background is 1.9 Kelvin. Slightly less than that, okay? Which therefore means also the energy density carried by this radiation of neutrinos is slightly less than energy density in the photons because the effective temperature is less.
Annihilation is also the time where it's decoupled.
Sorry?
So the decoupling time is the same as where the annihilation dropped at degree. So here I select two times.
Yeah, this is something different. So E plus and E minus annihilation I wouldn't call decoupling. Yeah, it's just a transition when electrons and positrons go from being a relativistic species to a non-relativistic species. And we often we picture this exponential suppression in the number density and energy density of electrons and positrons as an annihilation process. That the number of these particles get reduced because the kinematics now allow them to efficiently annihilate into photons. Okay.
And when do they decouple?
No, actually much. So okay, this decoupling here is a weak scale interaction. Electrons, of course, are electromagnetically coupled to the Standard Model. So they never decouple. They would never have decoupled. But what happens is before they annihilate. Okay? So the reason they are not there anymore is precisely because of the fact. If the electron in a world where the electrons wouldn't interact via QED with the rest of the Standard Model, they might have decoupled before they become non-relativistic. Okay? But that's not happening in this world. So that's why in this world the energy density in electrons and positrons gets reduced dramatically to exponentially small amounts before they would have a chance to decouple from the Standard Model, just because electromagnetism is such a strong force. Okay? You could do it for yourself if you go home. You could try to estimate what's the typical interaction rate for electromagnetically coupled species and ask at what temperature or time in the history of the universe would that thing decouple. And I bet it would be never. Okay? Just because electromagnetism is such a strong force. Okay? So this decoupling at around 1 second after the Big Bang happens because of weak scale interactions. And next time we're going to be looking at similar types of species that are even more weakly coupled than neutrinos, which would have decoupled even earlier. Okay?
But even though they are not decoupling, they do not contribute to the reactive temperature.
Sorry, they have their own temperature. Okay? So and as I'm going to show you in the next line, associated with the temperature is an energy density. So although they're decoupled from the Standard Model, the way we can still see those neutrinos is through their gravitational coupling.
I'm talking about the E-pass.
Yes? Sorry.
I thought decoupling means when the temperature is not
Yes.
So, yeah, I think the electrons are not still. When the electrons do not decouple with the photon, I think they are always at the same temperature.
No, okay. Maybe I'm going to get to that in a moment. Yeah, there's going to be an important moment which we call recombination and so on. So it's true that if you ask what's this interaction rate for electrons, interaction rates typically go as number density times cross section times velocity. And the velocity in a relativistic limit is the speed of light. So it's really number density times cross section like we had earlier. So the number density for electrons, so one important point maybe is that the number density of electrons exponentially shuts off when they have higher mass than temperature. And so that exponentially shut off in the number density will affect their rate of interaction. That's true. Okay? And so there will be this effect. But maybe let's discuss it later. Okay? But a decoupling when a particle already is non-relativistic is not very important because already at the time when it decouples, it only carried exponentially small energy density. While here the neutrinos were decoupling at the time when they were relativistic and carried a lot of the energy density of the universe, and they will maintain that energy density because they have decoupled. Okay. So in fact, we can calculate the fractional contribution in energy density of these neutrinos. So if we sum over all neutrino species each of their individual energy densities and compare them to the total radiation density, okay, this would be 3 times 7 over 8 times 4 over 11 to the 4/3 divided by 3 times 7 over 8, 4 over 11 to the 4/3 plus 1. Okay. So this, what I've written here is the energy density of 3 neutrino species because their fermions are 7/8, the temperature to the 4th power relative to the photons, which I've written as 1 here. Okay, the overall normalization will of course cancel here in this ratio. If you were to evaluate this, what you would find is 41%. Okay, so 41% of the radiation in the early universe is in the form of neutrinos. And that's, of course, a non-negligible amount, so you can ask, can we see the gravitational effect of this energy density? And I'm going to show you next time precisely how we see that energy density and have measured it recently. Okay? And therefore, we can test, is it really 3 neutrino species or maybe 4? Or do these neutrinos really behave like we think they behave in the standard model, or do they behave differently? Okay? All those kind of things we're going to be discussing next time. Okay, and then the third important event is recombination. So as the universe continues to cool, what happens at some point is that is it energetically favorable for electrons and positrons, protons, for electrons and protons to combine into hydrogen atoms and release a photon. Okay?
Why is it called recombination?
Huh?
Why is it called recombination?
Nobody knows. Yeah. It's a total misnomer. Okay. Yeah, it's a historical accident that happened way before I was born, so I would not be able to reconstruct. There's no sense to it. There was no way in which this. Yeah. Anyway, let's not talk about it. Okay. This is the first time electrons and protons combined into hydrogen. So there's no
You had hadrons forming earlier.
Sorry?
Maybe they just said we already had things combined earlier. Hadrons.
Maybe. I don't think they were thinking that much. I don't even know who to blame. I don't even know who came up with this. But it's okay. But in more colloquial terms, what's happening here is that the first neutral atoms are forming. Okay. At higher temperatures than this, the energies were too high, and collisions would ionize all of the plasma. This is the first moment when the temperature got low enough that we can have neutral hydrogen atoms. Slightly after that, we can have neutral helium atoms and so on. So what this also means, though, is that a lot of the electrons get captured into hydrogen, so the number density of electrons also reduces because they get absorbed into hydrogen atoms. So the number density of free electrons goes down. So what that means is that the scattering between electrons and photons, which is one of the most efficient processes that happens at early times, starts to become inefficient. Okay, and so photons decouple just because the number density of electrons goes down, and we saw that interaction rate is number density times cross-section. If I'm imagining the cross-section is just some fixed Thomson scattering cross-section between electrons and photons, as these electrons get absorbed by the protons, number density of free electrons goes down. The photons don't find any electrons anymore to scatter with, okay? And so these photons will start to decouple and free stream. And so these photons that are left over from this are called the cosmic microwave background. And this event here is also called photon decoupling. Or last scattering. It's literally the last time a photon scatters off a particle, and we can look for photons that are coming from the early universe that are just free streaming towards us. Okay, and famously, of course, this microwave background radiation has been observed. Okay, at this particular temperature. Right. Okay. So the detection of this cosmic microwave background and the way of studying small fluctuations in the cosmic microwave background have really made, this is where modern cosmology started. Without this experimental probe, we wouldn't be able to talk about all these things with that accuracy and confidence that we're talking about cosmology today. Okay, so that's why I want to spend a little bit of time describing for you the absolute basics of CMB physics, as I think even any particle physicist should know. Okay, of course it's a little bit of a subjective feeling how much of this type of physics a particle physicist should know, but this is the minimal level that I think a particle physicist should know. Okay.
About 15 minutes.
Yeah. So yeah, what I will do in these last 15 minutes is going to basically sketch out what the plan is going to be for next lecture. and then we're going to go through some of the details next time. So the first important thing that people noticed when they were looking and measuring this microwave background radiation, of course, famously, is the fact that it's not completely uniform. So I told you that it has this average temperature of 2.7 degrees Kelvin. But then when people were looking more closely, they found that the temperature varies as a function of direction on the sky at a level of about 10 to the minus 4. Okay? And so these variations are often also called CMB anisotropies. Because the sky is not completely isotropic, but has small variations as I'm scanning angles on the sky and look for temperature fluctuations, and I indeed have observed fluctuations at this 1 part in 10 to the 4 level. So there are hot and cold spots in the sky. Okay, so that's a good thing. If the universe had been really perfectly homogeneous, of course, that would have been a disaster. We wouldn't be able to explain how all of the structure in the universe had formed from something completely featureless. Okay, so there's an important period where these small fluctuations grow in time, and they form galaxies eventually. So fluctuations in the temperature, in fact, correspond to fluctuations in the density of these different species that we've been talking about earlier, and fluctuations in the metric that's determined by these matter fluctuations. So there were some primordial fluctuations in the density and in the space-time geometry that were leading to fluctuations in the temperature of the CMB photons, and those density fluctuations were growing over time to form bigger density fluctuations, which are what the large-scale structure of the universe, so galaxies. This process here is called structure formation. So what we're going to be discussing in the third lecture in a lot of detail is initial conditions for these primordial fluctuations. So I just want to say a few words now so that we can get them out of the way. So there are certain features of these initial conditions that we think are describing the initial conditions for our universe. And so in particular, there are 3 important features. So the first feature of the initial conditions is that they're so-called adiabatic initial conditions. Adiabatic means that these fluctuations in the different density components of the universe were not independent. Okay? They were somehow synchronized and can all be described by a single degree of freedom. So we have fluctuations in the electrons, fluctuations in the photons, fluctuations in the dark matter, but they were not independent fluctuations as they might have been, but they were somehow synchronized to each other. Okay? And there's a single degree of freedom that describes all of them together. And it also means that I can make a time reparameterization locally. I can change my time coordinate in such a way that I can pick a gauge where there's in fact no perturbations in the matter fluctuations. So this delta rho of A, so density in the universe is not a gauge invariant concept, density fluctuations. Okay, I can slice my space-time, in different ways and create or destroy density fluctuations. Adiabatic fluctuations are a special type of fluctuations where I can remove all of the density fluctuations with just one reslicing of time. Okay, that's of course not the case if I had just n random components. Then I could at most maybe remove one of them. What's special about adiabatic fluctuations is I can remove all components simultaneously. So I can choose a gauge where there's no fluctuations in the densities of the universe, and everything is eaten by the metric. So now the spatial slicings of the universe will be perturbed, and for example, the Gij component of the metric will be inhomogeneous. And so this famous curvature perturbation that I had at the very beginning of this lecture will appear as a local rescaling of the scale factor. So you can think of this as locally, as I go from one space in the universe to another space in the universe expands by slightly different amounts. And the measure of how different the universe expands at different places in the universe is this curvature perturbation, zeta. And so one very attractive feature of this curvature perturbation, why it's nice to pick this particular gauge for describing fluctuations, is that this curvature perturbation is conserved at early times. So if we go to early times, it also means that Fourier components of wave fluctuations are on very large scales, scales bigger than the horizon at the time, and this curvature perturbation is conserved on those scales. So it doesn't evolve. So large scales, I mean the momentum of a Fourier mode is less than the inverse of the Hubble horizon. Okay. So in terms of length scale, the wavelength of a mode is bigger than the so-called Hubble radius. On those particular scales, which is what the field experiences at very early times, this perturbation mode remains frozen. Okay. So this was proven by Weinberg, so it must be true. Okay. Okay. So this is nice because actually if you look at this theorem that Weinberg proved, there are some weak conditions under which this holds, but the conditions are restrictive enough that it applies even if you don't really know the energy component that filled the universe. So for example, after inflation, the universe reheated. During reheating, these modes, all the modes that we observe in the sky were living on very large scales. And it's because of this theorem that we trust that we can infer something about before reheating, conditions during inflation, because we can measure the curvature perturbation at late times, and we can use this theorem to translate it back in time, even through a period where we don't even know the equation of state of the matter filling the universe. Okay, so it's an extremely powerful theorem that allows us to confront inflation, for example, to observations. If it wasn't for this theorem, we wouldn't be able to say those things with a straight face. Yeah. Yeah, there's always going to be one mode called the adiabatic mode that does satisfy this, but there will then be additional so-called isocurvature modes, and then it becomes a question how the observables that you measure on the sky are related to the adiabatic mode and the isocurvature modes. There could be a linear combination of the two, and then you lose predictivity. Okay, in cases where the adiabatic mode, the initial conditions are adiabatic, then the adiabatic mode is the dominant growing mode that we then also observe in everything every measurement we make. Yeah, and so it's the simplest type of initial condition because it's very predictive. There's one mode that describes all scalar fluctuations, and the fluctuations in the CMB and the fluctuations in the distribution of galaxies, and all of those things are determined by this one fluctuation mode. Okay. Yeah.
When you say that this is just a gauge, is that neutrality, or is there actually going on?
Yeah, I mean time and space reparameterization. I consider that a gauge transformation. Okay, and so by choosing a specific coordinate system, I'm picking a specific choice of gauge. Okay, and so this gauge is sometimes called co-moving gauge because I'm or uniform density gauge, because I've chosen a gauge where there's no fluctuations in the density. Okay, so this is one particular property of the initial conditions that we're going to be assuming. A second condition is that the fluctuations are Gaussian. In fact, in the second half of my lectures, I'm going to be dropping that restriction on the fluctuations being Gaussian, and we're going to look for small deviations from Gaussian. But to begin with, let's assume this idealization where the fluctuations are perfectly Gaussian, meaning that this probability distribution that we had at the very beginning over there was a Gaussian probability distribution. And for Gaussian distributions, of course, you know that everything can be expressed just in terms of a variance or two-point function. And so the same applies here. So two-point correlation function, or the power spectrum in real space, describes the entire statistics. So if I look at the correlation between a Fourier mode k and a Fourier mode k prime, this is first of all proportional to a delta function of k minus k prime. So there's only going to be correlations between Fourier modes with equal Fourier vectors. And that's a consequence of the homogeneity of the universe. Then there's a momentum-dependent constant of proportionality, which is the power spectrum. So it depends on momentum, but it can only depend on the magnitude of the momentum, not on the direction. And that's a consequence of the fact that the universe is statistically isotropic. There's no preferred direction, so this power spectrum has to be a function only of the magnitude of these waves and not their direction. And then it's conventional to factor out a 2 pi squared over k cubed. Because 1 over k cubed is in fact the dimension of this 2-point correlation function. So one is factoring out this overall dimensionally dependent factor. So this is often then also called the dimensionless power spectrum. It doesn't have dimension. And also if the fluctuations have a special property, which is going to be the third property of these initial conditions, if they're so-called scale invariant initial conditions, then this form of the power spectrum as I've defined it is just a constant, meaning it becomes independent of momentum. That's what we mean by scale invariant initial conditions. Okay? This 1 over k cubed, if you do a Fourier transform of this power spectrum to get a real space 2-point correlation function, in 3 dimensions, what does 1 over k cubed transform into for a 2-point function? How does it, between x and x prime? If I were to do the Fourier transform of the power spectrum, I get a 2-point function. How does it scale with x and x prime? Not just a constant. By dimensions, yes, but functionally. Logarithmically, yeah. So it would be log x minus x prime. So the 2-point function between a curvature perturbation at position x and a curvature perturbation at position x prime scales as log x minus x prime, absolute value, okay? And that's what we mean by scale invariance in real space, and it translates into 1 over k cubed in Fourier space. Okay, for the first half of these lectures, this is going to be good enough. We're going to be assuming perfectly scale invariant initial conditions. In the second half of the lecture, we're going to be talking about slight deviations from scale invariance. And then we will parameterize this power spectrum by an amplitude, AS. The S stands for scalar fluctuations. And then a small momentum dependence, k over k star, ns minus 1, where ns is called the scalar spectral index, which describes how far away I am from scale invariance. And so it turns out that the way this has been defined here, ns equals to 1 would correspond to exact scale invariance. Okay? Don't ask me why people didn't choose just ns, would be nicer. In fact, Juan tried to change it. So in his famous paper, he was using ns to kind of make the community change from ns minus 1 to ns. But not even Juan could do it. Okay? It was too much ingrained in the minds of cosmologists. So ns equals to 1 corresponds to scale invariance, unfortunately. In this case, star here is just some arbitrary reference scale relative to which I'm measuring this deviation from scale invariance. Okay? But as I said, in the first half of these lectures, I'm going to be assuming perfectly scale invariant fluctuations. So if we were to plot this power spectrum of zeta of k as a function of k, in fact, will be very nearly constant, but it will have a slight tilt towards, this corresponds to large scales, small k. And this here would be small scales. And there's a little bit more power on large scales than on small scales, we now know. Okay? And that corresponds to dynamics during inflation. Because the energy density during inflation decreases, that adds a little bit more power on large scales than on small scales. Yeah, exactly. Okay, so the challenge for the next lecture is going to be to take this initial nearly scale invariant power spectrum and ask what does it evolve into. And in particular, we want to know what does it evolve into in terms of a two-point function of temperature fluctuations in the sky. And of course, there's a famous plot like this. Delta t at one point compared to delta t at another point has this type of shape. I'd like to explain to you why this shape and not some other shape. And also the distribution of galaxies, the power spectrum as a function of k for the delta rho of matter has also a specific shape. I won't tell you why this shape because we won't have time. Okay, I'm going to be focusing on this. So what we'd like to do is we'd like to start with nearly scale invariant initial conditions, evolve them forward in time, and see that they evolve into something like this. And in the process, we will understand the physics of these fluctuations very well. We can then ask, how does this shape here change if we change the physics? If we add some beyond the standard model aspect to this. Okay? So I'll do that tomorrow. Yeah.
So as you said, CMBM is also basically to structure formation.
Yeah.
So how to this? So can you actually measure
Yeah.
of like the present universe on large scale and actually see it like or something else?
Indeed. So in fact, people started to get worried. So people first, 50 years ago, almost exactly 50 years ago, people discovered the monopole. The average temperature 2.7 degrees. And then ever since, they have been looking for these deviations. And they started to get worried because 10 to the minus 4 is basically the last moment where the fluctuational amplitude is large enough for gravitational collapse to form galaxies fast enough. Okay? It wouldn't have been a problem if it had been 10 to the minus 3, because we can then form galaxies even faster. But 10 to the minus 4 is like the last moment where the amplitude is large enough so that if we just then evolve forward, the gravitational collapse is exactly what we expect. And then in fact you can measure galaxies not just today but like at earlier times, and you can trace the evolution, this growth, and it all hangs together perfectly. Okay.
So it's literally just measure the density of galaxies in the present.
Exactly, as a function of scale. You would basically measure this curve here. Yeah. So there's a specific feature here because the universe goes from radiation to matter, and that's what creates this feature here and so on. I can tell you later. So this has also a characteristic shape and has a characteristic amplitude. And you can ask, how does this spectrum evolve into this? Well, this is a spectrum of photons. This is the spectrum of dark matter, basically. But they're coupled to each other. So you know that there's some amplitude of photon fluctuations that has to correspond to some amplitude of dark matter fluctuations. They're both basically 10 to the minus 4. And you can ask, how long does it take for 10 to the minus 4 on the just collapse of gravity to become order 1 fluctuations, like we see around us. So yeah, you can do very, very specific tests. We don't know. So that depends, of course, on the neutrino mass splittings. Okay. I think we know at least one of them has to be non-relativistic today. But it became non-relativistic just very recently. So for our story, because our story is primordial cosmology, and primordial means everything before the CMB, say, let's define it that way. For that story, the masses of neutrinos, as we know, as much as they constrained now, is small enough that they're relativistic at that time. And there's some effect that they then have when they become non-relativistic, and in fact that also has been seen in the CMB. So in fact, one of the best measurement of the absolute mass scale of neutrinos, not just the differences in mass squareds. Yeah. So as you know, of course, the oscillation experiments only measure differences in mass squareds, while cosmology, in fact, becomes sensitive to the sum of all the neutrino species. And so they have seen a non-zero value for the sum of all species, and the best constraint, in fact, no, sorry, they have not seen that yet. They have an upper bound on that total mass, and they might soon see an absolute mass scale for all of the neutrinos.
One more. Yeah. For the CMB measurement, how much is very measurement and how much is what we get?
Of this?
No, the upper this graph.
How much of this graph is measurement?
Yeah.
Sorry, but no, I was joking. So maybe you can repeat.
Yeah. In which
Oh,
like we guessed.
oh, very good. Yeah, so so in fact, if you go to my notes, you will see actually the latest Planck map. Beautiful. Yeah, you see all the structure. But there is that map has been cleaned a little bit, okay? Because what usually, if you look at the raw data, not the cleaned map, you will see a band that stretches across this map that doesn't look like the CMB. And in fact, it's not. What it is just our Milky Way. Yeah. So in this particular projection, the Milky Way would stretch across the sky like this, and we can't make a measurement of the background radiation because it's blocked by the dust of the Milky Way. So you can correct a little bit for it, and then what you actually see when you see these beautiful maps by Planck is in that region they put simulated Gaussian CMB in there. So that part is not an actual measurement, and it corresponds to 30% of the sky. So 70% of the sky is truly measured, honest to God, and of course that part of the sky is being used for analysis, like this plot. Okay, and then there's 30% which we'll be never able to measure because of the galaxy.
All right, well, let's take our break. We'll come back at 3:45, and let's thank Daniel.
Sure.
So